So we discussed the capacitors, and we have this little form, the schematic, which says plus plus minus minus, and the battery here plus minus, and then capacitor 1, capacitor 2 plus plus, and minus minus, and then we have the circuit. Okay, and across these we have the voltages V1 and V2. So what is going on is this is the situation where we have these in series, and the circuit can be expanded to a possible number of capacitors. Okay, so the charge basically Q1 is equal to Q2 up to Qn is Q. Okay, there's no splitting of the charge, it's the same, but there is this splitting of the voltage across the capacitor. So V1 plus V2 plus up to Vn gives us V, the voltage, and this is the voltage across all the capacitors in total. And we know that Q is equal to CV, capacitance into voltage, and V is equal to Q by C. So V1, Vn is basically Qn by C, which actually means that we have a situation where V1 is equal to Q1 by C and V2 is equal to Q2 by C. Yes, so the Q by C equivalent is equal to Q1 by C1 Q1 by Cn, Q1 by C1, Q2 by C2, so plus Q2 by C2, and it goes on to Qn by Cn. So we take Q by C equivalent here on the left and Q as common. We're left with 1 by C1 plus 1 by C2 plus up to 1 by Cn, the nth capacitance, the nth capacitor in the circuit. Q cancels out on each side of the equation, so C equivalent is equal to the sum of 1 by C1 plus 1 by C2 plus up to 1 by Cn, and I hope it is legitimate. It's very much the general form for the series capacitors in series. And now the capacitors in parallel. Now we have the capacitors in parallel. And the situation is somewhat like this: plus plus minus minus, here 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 here, plus minus here here here. Okay, so now we have this C1 here and C2 here, and we have this voltage difference. It's actually V across the whole set, and so what we have is basically the splitting of the charges. So here we have this Q1 here, we have Q2, and this can go on if you want to expand the circuit. So V1 is equal to V2 is equal to up to Vn is equal to V. Voltage is the same, charge changes, so Q is equal to Q1 plus Q2 plus up to Qn depending on the number of capacitors. Okay, so Q is equal to CV, Qn is equal to CnV. Okay, Q is equal to CnVn. Q1 is equal to C1V1, Q2 is equal to C2V2, and so on. So the setting is C equivalent V, which is the equivalent capacitance for the whole circuit, times the voltage. This becomes C1V1 plus C2V2 plus up to CnVn. So C equivalent V is equal to C1V plus C2V plus up to CnV. V can be taken out. C equivalent V is equal to V into C1 plus C2 up to Cn. V cancels out on both sides. So C equivalent in this case is C1 plus C2 plus up to Cn depending on the number of capacitors in the circuit in parallel. Okay. So now energy stored in a capacitor. Energy stored in a capacitor. So potential difference average is equal to 0 plus V by 2 is equal to V by 2. Energy is equal to charge into potential difference. Charge times the potential difference. Okay. Energy is U in this case, and charge is Q, and potential difference is V by 2. So the situation is U is equal to QV by 2. So this is the situation here. And Q we also know that is equal to CV. Q is equal to CV. So this is 1 and this is A here. We make this substitution. U is equal to CV dot V by 2. U is equal to CV square by 2. And there's one more thing which you can do. The V is equal to Q by C from A. So this is B. So we can put it here if needed. U is equal to C into Q square by to C by 2 Q square by C square. This gives us Q square by 2C. This becomes a form. Square of charge by 2 times the capacitance equal to the energy stored in a capacitor. Either this or this, or rather I will prefer this one because of its practicality, but everything depends on what situation we are faced with. So energy in terms of field now. Energy in terms of field, V is equal to ED, electric field into distance, is equal to voltage. Capacitance is equal to C, and C is equal to A epsilon naught epsilon R by D. Okay. U, the energy, is equal to Q square by 2C, or CV square by 2. CV square by 2. CV square by 2, and U becomes A epsilon naught epsilon R by D times ED square by 2. Okay, the situation is U is equal to A epsilon naught epsilon R, electric field E. Let's make things clear here. ED square, this also is ED, square it down below, and the situation becomes something like this: epsilon naught E square AD by 2. So this becomes an equation of interest. this situation is slightly complicated, but we won't stop here and we will get over to the next topic, which is resistance. And for resistance, if we are supposed to define a form, we need to know that distance resistance final minus resistance initial is directly proportional to resistance initial, and it's also proportional to this difference is also proportional to temperature. Combining the two, R minus R naught is proportional to R naught T. RF is proportional to uh, RF. Uh, RF minus R naught is equal to, now putting the constant of proportionality alpha R naught T. So RF or RT can be used interchangeably because resistance and a certain temperature to the standard one is the final in this case. So what we do is we simplify the notations and we